Welcome to GTC and thank you for joining us today. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets you can use. All the windows on your screen are resizable and movable. If you have any questions during the webcast, you can submit them through the Q&A window to the right of the slides, and we will try to answer these at the end of the event. A copy of today's slide deck will be available in the GTC session catalog. You can find additional answers to some common technical issues located in the Help widget at the bottom of your screen. An on-demand version of the webcast will be available approximately 1 hour after the webcast and can be accessed in the session catalog. Now, without further ado, we'll turn the event over to our speaker to begin the presentation.
Hello, everyone. Thank you for joining today. My name is Chintan Shah. I'm the product manager at NVIDIA, and I manage a few of our AI toolkits. Today, I'm going to talk about Transfer Learning Toolkit and how it can be used to accelerate development of vision AI applications. First, let's look at some challenges. There are several challenges with training an AI model. First, you need deep learning expertise. That means learning about one or more of the deep learning frameworks, like TensorFlow, PyTorch, Caffe, etc. Also, you need a knowledge of deep learning architecture. Second, all the training frameworks are geared specifically to improve accuracy. Although training accuracy is very important, you also need to optimize the network for inference performance, especially if the inference needs to run on a small embedded device on an edge. And finally, to train, you need a data set, and sometimes a rather large one, if you want to train accurately. Collecting a large amount of data set is expensive and very time-consuming. This can significantly increase development time and cost. To tackle the challenges mentioned in the previous slide, we have created Transfer Learning Toolkit. Transfer Learning Toolkit, or TLT, is a simplified AI training toolkit to reduce training time and reduce your total time to market. If you use our highly optimized pre-trained model, you can reduce your development time by up to 10x, from 80 weeks to 8 weeks. To build an AI model, you need to collect and label data sets. This process is very time-consuming, and depending on your use case and the accuracy, it can take months. If you use one of our pre-trained models, which is trained on millions of images, you can reduce this effort from months to weeks. Next, TLT offers model pruning to optimize the model for inference. Using inbuilt pruning and quantization, you spend minimal time tuning and optimizing, which, if you were to train from scratch, you can expect to spend months fine-tuning your model. Lastly, all models from TLT can be directly integrated into DeepStream SDK, NVIDIA's streaming analytic toolkit. On the other side, developers might spend weeks deploying the model into a video pipeline. TLT doesn't require any special AI skills. The zero coding framework makes it easy for non-AI experts to get started. It reduces the barrier of entry for anyone who wants to get started building AI apps. For advanced users and data scientists, TLT offers knobs and customization to help you prototype faster. TLT supports training for object detection, classification, and instant segmentation network, with other novel model architecture planned for our future release. Here's the entire TLT software stack. Starting from the top, TLT can be used to apply transfer learning to add new classes to an existing model. It can help with scene adaptation, transferring weights from one application to another, adapting to a new point of view or a camera angle. Under this layer is our core toolkit. To train with TLT, we provide 40+ pre-trained models available on NGC, NVIDIA GPU Cloud Registry. Models are available for object detection, image classification, and segmentation. These models provide a good starting point for someone looking to start their training. TLT consists of few simple configurable steps to train. This includes data preparation and augmentation, training, and pruning. I'll cover the entire workflow in detail in this webinar. Users only need to modify an easy-to-use configuration file to get started. The toolkit sits on NVIDIA CUDA X stack. This includes all the lower-level libraries at NVIDIA, such as CUDA, cuDNN, and TensorRT. And finally, at the bottom are the NVIDIA computing platforms. Models can be trained using TLT on NVIDIA Power Workstation, DGX Box, which are supercomputer in a box, and in the cloud with NVIDIA GPUs. For inference, models can be deployed on any NVIDIA platform, from embedded Jetson devices to large servers. The table in the slide shows all the different classification, detection, and segmentation network architectures that are supported in TLT. TLT 2.0 is our latest release, released in August of this year. For image classification, you can train all the popular resident models, VGG, GoogleNet, MobileNet, SqueezeNet, and DarkNet architectures. Developers can choose model architecture depending on use case, accuracy, and deployment platform. For object detection, TLT supports the extremely popular YOLO V3, faster RCNN, and SSD. It also supports NVIDIA's own DetectNet architecture, as well as open source RetinaNet and DSSD. Developers can use any combinations and permutations of detection and backbones. Finally, starting with TLT 2.0, we're introducing training support for instance segmentation model using the mask RCNN architecture. Instance segmentation is useful when you need pixel-level accuracy, which you do not get with object detection. To kickstart training, we provided pre-trained weights for all these models, which are trained on open image public dataset. Instead of starting from scratch, developers can build their model using the pre-trained weights. This reduces training time when compared with training from scratch. In addition to the networks shown on the previous slide, we have also launched production quality vision AI models that are highly accurate and are freely available on NGC. These are application-specific networks that can be retrained with TLT or deployed out of the box. These are trained on millions of our own proprietary images. We feel this provides an excellent starting point for an application. The people-led model is trained to detect people in many different environments. I'll go over some KPIs for this model later in the webinar. The traffic cam-led model can recognize cars, bikes, pedestrian, and road signs. This is very useful for a smart city application where you want to track cars on the road for traffic analysis. Dashcam-led model is collected on images from a dashboard inside the car. Useful for auto application where you want to create an alert based on what is happening in front of the car. The vehicle type and vehicle make are useful for smart city application where you want to categorize cars on the road. Finally, the face detect IR model is an extremely accurate model to detect faces from a low light infrared camera. This can be used for auto application to monitor drivers inside the car. We provide a pruned model and an unpruned model on NGC. The unpruned version can be used with Transfer Learning Toolkit to retrain. The pruned version is the high performance model for inference. For smart city and smart retail type of application, we feel this model will make your job of training accurate AI much easier. One of the key features that we have in TLT 2.0 is quantization-aware training. Typically, models when represented in lower precision make them compute efficient. Int8 models are significantly faster than running inference in floating point. However, quantizing FP32 or FP16 weights to Int8 post-training can oftentimes reduce model accuracy due to quantization errors. With the QAT feature of TLT, quantization error is accounted for during the training step, so that when you export an Int8 model, the error is significantly less. This provides comparable accuracy on an Int8 model as a floating point model. With QAT in TLT, developers can achieve up to 2x inference speedup without sacrificing accuracy. To give you an example, the people-led model is trained on dataset, which makes it difficult to accurately quantize post-training. In the table, you can see that when we quantize post-training, we are losing about 20% in terms of accuracy. But when you use QAT, the accuracy loss is within 1%. The key takeaway is that quantization-aware training helps you train DNNs for lower precision Int8 deployment without compromising on accuracy. We have a developer tutorial that shows how to train using QAT with Transfer Learning Toolkit. Another feature that we've released in TLT 2.0 is support for automatic mixed precision, or AMP. AMP enables training using mixed precision, so some ops can run at FP16 precision versus running at FP32. A lot of newer NVIDIA GPUs comes with tensor cores, and FP16 ops can run on tensor cores to take advantage of the entire GPU. Now with TLT, you can take advantage of running your math-intensive operations on tensor cores. Benefit of AMP are you can speed up math-intensive operations. You can also speed up memory-intensive operations because FP16 uses half the bytes as FP32. This results in overall reduction in memory footprint. Finally, with AMP with TLT, you can speed up your training time by 1.5x. AMP and TLT can be enabled by simply changing one of the environment variables. More information on how to enable AMP can be found in the TLT Getting Started guide. Another key computer vision technique that we have added in TLT 2.0 is instance segmentation. Now you can train instance segmentation models using NASCAR CNN. It's as easy as training other models. Instance segmentation provides a pixel-level accuracy by creating fine-grained segmentation masks around the detected object. The application for segmentation are an AI-powered green screen where you want to blur or change the background of the frame, or for autonomous driving where you want to segment road and background, or in the case of manufacturing, identifying microscopic level defects. There are numerous use cases for segmentation. Data annotation for training data is supported in the popular COCO format. We also provide an out-of-box example of deploying the model with all the post-processing and overlay using DeepStream. This makes the deployment of your AI model easier. Currently, you can use any of the ResNet backbones with NASCAR CNN. We also provide a detailed developer tutorial on training NASCAR CNN model. It's a step-by-step guide of training open source COCO dataset. As mentioned earlier, TLT comes with highly optimized pre-trained models. One of our main models is PeopleNet. This model is trained to detect people in a crowded environment at different distances and at different camera angles. This model can be used to build applications such as people counting, occupancy analytics, heat mapping, etc. The model is trained on almost 900,000 images. As the name suggests, this model is highly tuned to detect people, and we have used almost 9 million objects of people class. The training dataset consists of a mix of indoor, outdoor, and office environment, and with camera at 5 feet, 10 feet, and 20 feet from the subject. This produces a very good model to analyze crowd and people. We have released a ResNet 18 and a ResNet 34-based model. The evaluation KPI table shows the accuracy for both models at different distances from 5 feet to 20 feet, including indoor office use case. In addition to the accuracy, this model is highly optimized for inference performance. The bar graph shows the inference performance of both models on Jetson Nano, Xavier NX, AGX Xavier, and T4. The performance is using intake precision for inference. In general, ResNet 18 model is about 30 to 40% faster than ResNet 34, with slightly less accuracy. This gives developers option to choose between a higher accuracy model or a higher performance model. You can get more details on the model from our model card on NGC. We've used TLT for a very important COVID use case to detect if the person is wearing a face mask or not. Now, let's jump into how to build this model with TLT. We built a complete end-to-end face mask detection model using TLT and deployed on DeepStream. In this day of COVID-19, there are numerous use cases that businesses can benefit from automating if patrons are wearing a face mask or not. To start with, we trained a two-class object detection model, one to detect faces with masks and other to detect faces without masks. For training, we used several open datasets with annotation. For model architecture, we chose DetectNet v2 with ResNet 18 backbone. For this, you can use either the people-led model or a ResNet 18 pre-trained weights from NGC. Our dataset consisted of 4,000 images with almost 50% annotation of faces with mask and 50% without. We fine-tuned the model to improve accuracy and inference performance by model pruning and quantization. In the next few slides, I'll go over how to build such a model, and you can follow our recipe to build your own face mask detection model. We have also open sourced the entire recipe on GitHub with a step-by-step developer blog. First, let's look at the demo of what the entire application looks like. In the demo, it will detect a person's face and if the person is wearing a mask or not. The training workflow shows the steps from downloading the dataset to building the trained model. Once you have downloaded the dataset, first step is to convert to Kitty. TLT currently accepts annotation in Kitty, and we provided a script on our GitHub repo to convert the dataset. This happens outside the container. Once you have the dataset in the desired format, you pass the data to TLT to prepare the dataset for training. In this step, data is converted to TF records. TF record makes it easy to load data faster. Once generated, you can use it across multiple training experiments. After preparing dataset, next step is to train. Here you will download one of the pre-trained models from NGC as a starting point. After you train, you prune the model, reduce the complexity and size of the model, and validate it to see if it hits the accuracy as expected. Once validated, quantize and export the model. Finally, you will have a trained model that is accurate and high performance. You can deploy this model on any NVIDIA GPU. Now, let's go through each block in the workflow. The first step is to get the data in the training format that TLT expects. First, take all the different annotation formats and convert to Kitty. Second, TLT data loader requires all training images to be of equal width and height. For this experiment, we are using selective images from 4 different datasets. Take of medical and MATLAB are used for faces with mask. FTDB and wider face is used for faces without mask. Our total training dataset consisted of about 4,000 images with almost even distribution between both types. The data to Kitty script provided on our GitHub page can read any of these datasets and convert it to the Kitty format and the desired resolution. Alternatively, you can also use the TLT's augment tool inside the container to scale the images before training. For our training experiment, we chose 960 by 544 resolution because that gave us the best accuracy and performance. Now that you have your data set that is compatible with TLT, let's move on to training. TLT is a zero-coding framework that makes it easy for anyone to get started. Developers do not have to learn about deep learning frameworks or have to do any coding. TLT is configured using simple protobuf spec files, which can be used to specify datasets, training hyperparameters, evaluation KPI, and inference. The dataset spec file helps with loading the data, splitting the dataset between training and validation. The training spec file offers configuration parameters to select which dataset to use for training, which dataset to use for validation, which pre-trained model architecture to use, which hyperparameters to tune, and other training options. The training option varies between model architecture. The evaluation spec file allows users to select which dataset to use for evaluation, as well as evaluation metrics. And finally, the inference spec file is used to select options to run inference using TensorRT on trained model. This is an optional step, but we highly recommend running inference on a handful of images before deploying the model. Detailed information of all the available options can be read from TLT Getting Started documentation. The first step of TLT is preparing your dataset, creating training and validation data, and converting the dataset to TF records. This is extremely useful when you are training on hundreds of thousands of images. TLT allows 2 types of datasets. Common training and validation dataset, the TLT will split randomly during dataset convert, and separate dataset for training and validation that is chosen by the user. Splitting dataset randomly might be useful for quick prototyping and or when you're experimenting with different datasets or you're not sure how to split your data. To randomly split based on some percentage, change the partition mode parameter to random in the dataset spec file. Also, in the training spec file, set the validation for parameter to 0 to use the randomly split dataset. The TLT command to convert the dataset is called TLT dataset convert. The output will be 2 TF records, one for training and other for validation. On the flip side, if you want to use separate dataset for training and validation, you run 2 separate TLT dataset convert on each dataset. This will create a separate TF record for both. You use this validation dataset during training, specify this TF record using the validation data source option in the training spec file. Either options are acceptable depending on your dataset and use case. Now that you have prepared your dataset, next step is to use this for training. In the TLT workflow, start by downloading a pre-trained model that you want to try. Provide this model along with your dataset to train. Once you do your initial training, next step is to evaluate on a completely different dataset that your training has never seen. If the evaluation accuracy is as expected, you move to model pruning, or else you go back to training again. Pruning will remove the neurons from your neural network that it doesn't believe contributes to the overall accuracy. Although not desired, model pruning will reduce your accuracy when you start removing neurons. You can regain the accuracy by retraining. This step is very similar to your initial training step. Only difference is you will start with a prune model to retrain. Once retrained on the same dataset, you send it to evaluation to assess the overall accuracy. Using the same test data and KPI as your initial evaluation, you check the overall accuracy. Once the accuracy after pruning and retraining has reached the desired level, now you have a model that is highly accurate, reduced memory, and highly optimized for inference. The training and evaluation spec files are used to configure each step in the workflow. Now, let's double-click into each spec file. Let's look at the training spec. Of the few things that you can configure in the training spec are the dataset, which dataset to use, and model, which pre-trained model architecture to use. In the dataset config, you specify the TF record path for training and validation data. You can also configure classes that you want to train over. For validation data, you can use the validation for option if you're using random split between training and validation. Or if you have a different validation dataset, then you can uncomment the validation data source option. For model config, arch parameter configures the model architecture. The options are ResNet, MobileNet, PGG, DarkNet, etc. For a full list of backbones that are supported, refer to the TLT product page or TLT documentation. The pre-trained model file sets the pre-trained weights to start training. If you're using the same spec file for retraining after pruning, just change the location of the pre-trained model to point to the prune model. The other important config is the training config. In training config, you configure the training hyperparameters such as the batch size of each forward and backward pass, number of epochs, learning rate, and regularizer parameter. You can also enable quantization of your training using the Enable QAT option. This takes quantization loss during the training run to improve int8 accuracy. Typically, you enable QAT when you are retraining after model pruning. You can also save how frequent you want to create checkpoints based on number of epochs. You have set the checkpoint interval to every 10 epochs. TLT supports variable learning rate with a soft start. The learning rate will start from min learning rate of 5 times 10 to the negative 6 at epoch 0 and slowly climb to the max learning rate of 5 times 10 to the negative 4 when it reaches 30% of max epochs. These values are configurable using learning rate option in the config file. Finally, other training options that you can configure are data augmentation, bounding box ground truth generator, and post-processing config. Some of the options might be different depending on the model architecture. The TechNet V2 offers the most options and flexibility for our advanced users. The evaluation spec is defined inside the training spec. This is used to evaluate the accuracy of the model during training and post-training. You can use the same configuration for both validating during training and model evaluation post-training. Change the dataset when you're evaluating the model using the dataset config option in the training spec file. But apart from that, all the other options can be similar in the spec file. For evaluation, TLT uses average precision and mean average precision metric, or MAP. The MAP is defined as per the Pascal walk challenge with MAP calculation using the sample method or the integrate model. The spec shown on the right shows the validation every 10 epochs, with first validation starting at the 10th epoch. The ground truth overall for both classes is set to 0.5. For other parameters, you can leave the default value that's provided in the sample spec file. To learn more about the different options, read the spec file chapter of the TLT Getting Started manual. Now that you have created your individual spec files, it's time to start training. To train, use the provided TLT train command inside the TLT container. This takes the training spec file as input, key, which is the encryption key that comes with the pre-trained model. This key is provided on NGC. You can also specify the number of GPUs to use for training. The training run dumps in elaborate logs, which shows total trainable and non-trainable parameters, training loss per epoch. This helps to see if and when our model converges. As specified in the training spec, it also prints validation cost and MAP metric on validation data every 10 epoch. To evaluate, use the TLT evaluate command and provide the evaluation spec file and the model that you trained. This will evaluate on a test data set and dump the evaluation logs, which shows the average precision across all the classes. For our use case, we have two classes, mask and no mask. One of the key benefits of TLT is model pruning, ability to reduce the overall size and complexity of the model without sacrificing accuracy. The graph plots the accuracy and model size with respect to pruning threshold on our mask, no mask model. The accuracy hovers around 85 to 86% until the threshold reaches about 0.6. At this point, the accuracy starts dropping off drastically. The model size line shows the size of the model scaled with respect to the unpruned model. As you increase the pruning threshold, the model size decreases. With pruning threshold of 0.6, we are seeing almost 8x reduction in the model size. Pruning threshold is something you will have to experiment to understand how much you can prune on your dataset without significant loss in accuracy. This is highly dependent on model architecture and dataset. The biggest benefit of pruning is a significant improvement in inference performance. The table shows the inference performance of our face mask detection model on Jetson NX with an unpruned and a pruned model. Our 8x pruned model provides roughly 2 to 3x increase in performance. The performance gain is directly correlated with the pruning threshold. Model pruning by itself reduces the accuracy. So the next step after pruning is to retrain the model on the same data set to hopefully regain the lost accuracy. This retrain and evaluate steps are similar to the model training and evaluation steps at the beginning of the training cycle. You can use the same training config file with few minor changes. Change the pre-trained model in the config file. Use the pruned model as a starting point for retraining. Also, you might convert sooner, so you could reduce the number of epochs. Use the same TLT train and TLT evaluate command for retraining and evaluation. Now let's look at some training KPIs for our face mask detection model. We tried two experiments, one using DetectNet v2 ResNet 10 backbone and another with the DetectNet v2 ResNet 18 backbone. For both experiments, we used a 960 by 544 as our input image resolution. We tried smaller resolution, but we got significantly lower accuracy. The overall accuracy on our 4,000 image data set of the ResNet 10 model is few percentage lower than the ResNet 18 model. Although the model accuracy is solid, there are several limitations to our model. The dataset consisted mostly of images with subject around 5 feet from the camera in good lighting condition. We haven't evaluated or trained when the subject is beyond 10 feet. Also, dataset consisted of mostly surgical masks, so accuracy on other type of masks was slightly lower. We encourage our users to extend upon this model to improve accuracy to cover more use cases. The last steps in our training process are quantization and model export. In quantization, the floating point weights are quantized to intake to run inference at a lower precision. This speeds up the inference time. We provide several methods in TLT to quantize. You can quantize post-training or do a quantization of our training or QAT, which we covered in the earlier section of the webinar. To calibrate, start with an TLT intake tensor file command to generate a calibration tensor. The calibration tensor file is a binary file that contains pre-processed training samples which can be used to calibrate the model. The input to the TLT intake tensor file is a dataset or samples that you want to calibrate on. Once you obtain this tensor file, feed it directly to TLT export. TLT export command will export an encrypted TLT model and an intake calibration cache. The calibration step is optional and is only required if you want to run inference at intake. The exported model can run on any NVIDIA GPUs. The inference will be using TensorRT, NVIDIA's inference runtime. The final step is to visually verify the TensorRT model and intake calibration provides the same accuracy as expected. This last step of validation is run using TLT infer, where you provide sample images to infer using TensorRT. Running inference inside the TLT container is an optional step, but very important. You create an inference spec file where you configure the target class, input image dimension, and bath size. You have an option of directly providing the eTLT model from model export step or convert to a TensorRT engine and provide the engine file for inference. If you provide the eTLT file, TLT infer will first generate a TensorRT engine before running inference. You can also provide the intake calibration cache for running inference using intake. To generate and overlay bounding boxes over the object, use the bbox handler config to configure post-processing clustering after inference. You can use this to configure confidence of threshold and the color of the overlay box. To run inference on the trained model, use the TLT infer command from the container. This takes directory of images as input and outputs a directory of images with bounding boxes and labels. This is useful for visual verification of TensorRT-based inference. This will mimic what the inference deployment on the edge would look like. Now that our model is ready and we feel confident, it's time to deploy on a real application. The encrypted model from TLT will work out of the box with DeepStream. DeepStream SDK, which is our streaming analytic toolkit for real-time AI-based analytics on video. DeepStream provides building blocks to take streaming video data in and applies AI on the pixels to generate insights. DeepStream SDK is highly optimized for performance and latency through the use of various hardware acceleration on NVIDIA GPU and zero memory copy between each stages. DeepStream makes it easy to go from model generation to deployment. This is a real time saver as developers don't have to spend time creating an application or ensuring that the model works as expected. DeepStream has all the pre- and post-processing required to run models. In addition, DeepStream provides lots of IoT features to create a scalable solution. To learn more about DeepStream and its latest features, visit the DeepStream product page. The table shows the real-time performance of our face mask detection model on various NVIDIA Edge devices, starting from Jetson Nano to Jetson AGX Xavier. This model works on GPU as well as on the DLA, in the case of Xavier NX and AGX Xavier. This helps customers increase the stream density on their hardware, which reduces total cost of ownership for you and your customer. This concludes my talk. To summarize, in this webinar, you learn about key features of TLT and pre-trained model and how it can help you reduce your development effort and time by up to 10x. Next, I went over the entire workflow of TLT from bringing your dataset to generating a trained model. TLT is a zero-coding framework which simplifies the process of getting started with creating vision-based AI applications. TLT operates on spec file to configure things like your dataset, pre-trained model, training hyperparameters, etc. The Getting Started guide provides detailed information on all the steps and options. Lastly, you learn about using TLT to create a very simple but an important model to detect if a person is wearing a mask or not. You learn how to fine-tune and optimize the model by applying model pruning and quantization. And then you learn how to deploy the trained model on DeepStream for inference on streaming video. You can use the information in the webinar and the blog to build upon our work, improve the model, or apply transfer learning to a different domain. So download TLT and the pre-trained models and get started building your Vision AI application. Before we move on to Q&A, I want to tell you about a few of our other webinars. We will have a DeepStream webinar at 9 a.m. today. And then we'll have a Connect with Experts session at 2 p.m. this afternoon. To learn more about other sessions, check out our GTC session catalog. Before we move on to Q&A, I want to highlight some resources for pre-trained models, TLT, and DeepStream. We have tons of developer resources like blogs, past webinars, and documentation that can help you get started. So now let's move on to the Q&A section.
Okay. Thank you everyone for joining this session. Chintan will now be answering questions. Hey, Chintan.
Hey, Nadia.
Hey.
All right. Thank you guys for joining the webinar. Go ahead.
All right. First question, does TLT have any limitations to use with Titan XP?
That's a very good question. So TLT as a tool does run on Titan XP or any NVIDIA GPU without any issue. The limitation comes from the GPU hardware itself. There's a memory limitation. So if you use a card that has a lesser memory, then you might have to lower the batch size than you would on, for example, a V100 machine. Also, Tensor cores aren't available on the Titan XP hardware, so you won't be able to use the AMP mode in TLT.
All right. Next question, is face detection model available on NGC?
Yes, there are several face detection models on NGC that we currently provide. You can use the face detect IR model, which is to detect faces in infrared. And then you can also use the PeopleNet model with the face class. The face mask detection model that you saw in this webinar is not available on NGC. We only provide a developer recipe to build your own models.
Got it. We have another question. What does batch size per GPU mean?
Yeah, so TLT supports multi-GPU, and when you use multi-GPU, you need to configure batch sizes per GPU. It's very important to, when you use a multiple GPU, to reduce the number of batch sizes per GPU. So this is useful for the multi-GPU setting. Next question.
All right. The next one is, how do you run the models in the Deep Learning Accelerator, DLA?
So DLA is a deep learning accelerator which is available on our Jetson AGX Xavier and Xavier NX, and all the models from TLT will work on DLA. One way and the easiest way to run it with the DLA, the models with the DLA, is to use DeepStream. And when you use DeepStream, you can enable the DLA using the DLA configuration option to run the models on the DLA.
Got it. Next question, can you please explain why would one want to prune the model and what are the specific benefits of pruning?
Yeah, very good question. So what pruning provides is it reduces the number of parameters in a network. And the result is it reduces the computational complexity of the model. This is extremely useful when you're deploying on an edge platform where you have limited compute, such as our Jetson line of embedded devices. So when you prune, the main benefit that you get is reduction in memory and improved in performance. And from some of the experiments that we have done on on the models that we showed today, we were able to get almost 5x reduction in memory and more than 2x increase in performance.
Thank you.
Next question.
We have another question. Where can we find mask detection model on NGC?
So currently, the mask detection model is not available on NGC. At the moment we only provide a developer recipe, and the developer recipe comes with scripts as well as a Jupyter notebook to get started. It walks through the data set that we have used to generate our model that was showed in this webinar. And we've also released a developer blog that you can to learn how to build the face mask detection model.
Thank you. We have another question on pruning. How much lost accuracy is typically regained after pruning by retraining?
Yeah, so the answer there is it kind of depends. It depends on the model architecture. It depends on the data set. And main thing, it depends on what was the pruning threshold. If you use a aggressive pruning threshold, then you might get a higher pruning reduction in memory, but you might not be able to regain it. So this is something that you will kind of have to experiment. It's kind of where you have to experiment different pruning threshold to see what is the minimum, what is the maximum pruning threshold that you can try that will regain your accuracy to what was before pruning.
Got it. We have one more question. What resolution is the video that was used to get the benchmarks on the comparison table?
What resolution is the video? The resolution of the video is a 1080p, and this was used with the entire pipeline was built using DeepStream. So the input video was a 1080p 30 FPS, and the pre-processing routine within DeepStream will convert the 1080p to the required resolution of the model. So I think in our benchmark we have shown a 960 by 544. So the 1080p will scale down to 960 by 544 or a different resolution if you're using a different resolution, and it will map it to the 1080p video. Next question.
Got it. And this will be the last question for today. Does TLT support quantization aware training?
Yes, it does. So QAT, or quantization aware training, is where you take the where you quantize it, and you take the quantization error during your training step. And what this provides is a much better accuracy when you quantize the weights to int8. So TLT does support QAT, and it's as simple as just turning on a configuration to enable QAT with TLT.
All right. Thank you, Chintan. Thanks, everyone, for joining the session at GTC. This session will be available on demand in the session catalog in a couple of hours. Have a wonderful day, and thank you again for joining us.
Thank you, everyone.